So we are still on chapter 12. Let us finish chapter 12. We're going to talk about planes and then talk about different surfaces. Chapter 12, 12.5, 12.6, objectives. We're going to talk about planes. So far we talked about lines, and then we saw different equations for lines. We talked about the vector equation for the line. We represent the symmetric equation for the line. Then we talked about parametric equation for the line. So we are all familiar with lines. The next thing that we're going to talk about are planes. So now we're going to talk about planes in the space. So I expect you to ask, how do we write equation of a plane in the space? Well, officially, to write equation of a plane, we need one point on that plane, and we also need a vector or a normal orthogonal line to the plane to write equation of a plane. We need two things. One, a point on the plane, and two, a normal line. There you go. So if we have a point on the plane, suppose this is our plane here, this is our plane, you have a point on that plane. Suppose this is point x sub 0, y sub 0, and z sub 0. And you also have your normal line, normal to the plane. We denote this guy by n. Well, the equation of the plane can be written this way. A times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 equal to 0. Normal vector n with components a, b, and c. So where does this equation come from? It comes from the fact that this line, this normal vector, is perpendicular to our plane. What's the meaning of that? It means that if I take 2 points on the line, so this is my x sub 0, y sub 0, and z sub 0, and this is another point on the plane, x, y, z. I can connect these two and construct a vector. This vector. So this vector has components x minus x sub 0, y minus y sub 0, and z minus z sub 0. Very well. And at the same time, I have the normal line or the normal vector to the plane. This is my n with components a, b, c. When we're talking about being normal, orthogonal, it means that the angle between these two is going to be 90 degrees. 90 degrees, what's the meaning of that? It means that the dot product between these two vectors is 0. So the dot product between a, b, c, and x minus x sub 0 y minus y sub 0, and z minus z sub 0 is 0. But we already know about the dot product. It means that a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 is 0. That's how we get equation of a plane. Example says, write equation of a plane passing through this point 2, 4, -1 with normal vector n equals to 2, 3, 4. 2, 3, 4. Okay, we have all the information that we need. We have our normal vector. It means that we have our A, B, and C. And we also have our points on the plane. So this is our x sub 0, y sub 0, and z sub 0. Okay, very well. Let's plug them in. We have 2 times x minus 2 plus 3 times y minus 4. And we have 4 times z minus -1 or z plus 1 equal to 0. Since you know algebra, we distribute 2, we distribute 3, we distribute 4, and try to simplify this. We get 2x minus 4 plus 3y minus 12 plus 4z plus 4 equal to 0. So it means that the equation of the plane is 2x plus 3y plus 4z. And cancel out -4 and 4 equals to 12. Okay, here we have 2x plus 3y plus 4z equals to 12. This is our plane in the space. Of course, we can change these to change the measurements. And as you can see, your plane continues in all sides. But for simplicity, we just try to use smaller range to have a better visualization of our plane. Okay, so sometimes they have cases that we don't have a nice normal line here, and we need to find that normal line. Like what? Like this case here. The question says, find equation of a plane passing through 3 points. Well, okay. What should we do here? Right? Equation of a plane that passes through these points. What points? P, 1, 3, and 2. Q, 3, -1, 6. And finally R, with coordinates 5 to 0. 5 to 0. So we have 3 points in the plane. Suppose you have P here, Q here, and R here. So in general, when you have 3 points in the plane, your job is to find the normal vector. What is the normal vector? To find the normal vector, you're going to construct 2 vectors on the plane, then find the cross product between them, and then we have our normal vector. So the first vector, then the second vector, then their cross product is going to give you the normal vector. So N is the cross product between 2 vectors in the plane. So step by step, you're going to find the normal vector. So let us find PQ. Then we find PR. Then we need to find the cross product between PQ and PR. PQ. So we are constructing a vector. 3 minus 1, comma negative 1 minus 3, comma 6 minus 2. So our first vector is 2, negative 4, and 4. PQ, the very first vector in the plane. Then PR, 5 minus 1, 2 minus 3, 0 minus 2, which is 4, negative 1, and negative 2. So we found the second vector, and now the cross product between them is your normal vector. To find a cross product, remember that we have I, J, K on the first row. On the second row, we have our first vector, which is 2, negative 4, and 4. On the last row, we have the last vector, which is 4, negative 1, and negative 2. Okay, so it's going to be I, 8 plus 4 minus J, negative 4 minus 16 plus K, negative 2 plus 16. Okay, our normal vector is 12, 20, and 14. Take 1 point on the plane, like P1, 3, 2, and you have your normal vector. Just write equation of the plane. So we have 12 times x minus 1 plus 20 times y minus 3 plus 14 times z minus 2. Set it equal to 0 to write equation of the plane. Well, here we can divide everything by 2. Why not? We get 6 times x minus 1 plus 10 times y minus 3 plus 7 times z minus 2 equal to 0. Then distribute 6. We get 6x minus 6 plus 10y minus 30 plus 7z minus 14 equal to 0. So here we have negative 20, negative 50. You get 50 back on the other side. So you have 6x plus 10y plus 7z equals to 50. This is equation of the plane passing through these 3 points. Very well. So we talked about lines, we talked about planes. Now I expect you to ask, how do we find the point of intersection between a line and a plane? Question. Find the point of intersection between the line, which is given to us as x equals to 2 plus 3t, y equals to negative 40, and z equals to, well, we have 5 plus t, and the plane. Equation of the plane given to us as 4x plus 5y minus 2z equals 18. Okay, perfect. Well, here you have 3 variables, 1, 2, 3. To solve the equation, we need to write everything in terms of 1 variable. So if you look at your line, everything is written in terms of t. Just substitute everything here. So substitution. Substitution of line into the plane. Okay, plane is 4 times x. What is x? X is 2 plus 3t plus 5 times y. What is y? Negative 40 plus negative 2. So let's write down minus 2. Z, which is 5 plus t. 5 plus t. On the right-hand side, we have 18. Let us distribute 4, distribute 5, distribute negative 2, and solve for t. So here we have 8 plus 12t minus 20t minus 10 minus 2t equals to 18. So here we have 10t minus 20t, negative 10t. Here you have negative 2. On the right-hand side, you get 20. So t is negative 2. Okay, let us plug in t into the equation of the line to find the coordinates for the point of intersection. Our x coordinate is 2 plus 3 times negative 2. Y is minus 4 times negative 2. And z is equal to 5 minus 2. So our x is equal to negative 4. Y is equal to 8. And z is equal to 3. So the point of intersection has coordinates negative 4, 8, and 3. So let us take a look at our plane and the line. So equation of the line. Let's write it down. The plane first, so the explicit surface that we have. have 4x plus 5y minus 2z, which is equal to 14. So this is our plane. Let us add the line. Two plus 3t negative 40, and finally 5 plus t. And this is our line. Very well, so let's continue this. And let us expand our, this is 14, right? Not 41. Okay, this is negative 10, and then 10. Need to have more. Need to expand this so we can actually see the intersection between these two. Okay, here we go. So as you can see, this line passes through the plane. And we found the point of intersection between the line and the plane. Very well. So what if you're interested in analyzing relation between two planes? So when it comes to planes, we have two cases, two situations. Planes are parallel if and only if their normal lines, normal vectors are parallel to each other. Their normal vectors are parallel. So you have two planes. This is your first plane, and this is your second plane. When these two planes are parallel to each other, it means that their normal vectors are parallel. So n1 is parallel to n2. So if you find the components of n1 and n2, you see those components, if you do the division between the corresponding components is equal to a fixed number. If you have intersecting planes, you can easily find the angle between those two planes. When planes are intersecting, we can find the angle between them by using their normal vectors. Cosine theta is equal to n1 dot product n2 divided by the magnitude of the first vector times the magnitude of the second vector. And we're going to take the smaller angle between these two vectors. For example, Suppose you have two planes. And you're interested in finding the angle between these two planes. The very first one is x plus y plus z equals to 1. And the second one is x minus 2y plus 3z equals to 1. So the very first normal vector is n1 equals to, we're looking at the coefficients here, 1, 1, 1, and n2. The second normal vector is 1, -2, and 3. Following the formula, cosine theta is equal to the dot product between these two normal vectors. 1 times 1, 1. 1 times -2, -2. 1 times 3, 3. Divided by the magnitude of the first vector, which is square root of 3, times the magnitude of the second vector, 1 plus 4, 5, plus 9, 14. Okay, so it says cosine theta is equal to 2 divided by square root of 42. Now to find theta, we need to find the inverse of cosine of this fraction using calculator. By using your calculator, you can find this angle, which is around 72 degrees. This is the angle between these two planes. So let us visualize these two planes, and we're going to check to see if they are actually intersecting or not. So the first plane is x plus y plus z. Which is equal to 1. And the second plane which is x minus 2y plus 3z equals to 1. Okay, perfect. So as you can see, these two planes are intersecting planes. And we're finding the angle between the normal vectors. Find the distance between, for example, a plane from another plane, a point to a plane, or a point from a line. So the distance formula says, if you have a point, let P, x1, y1, z1 be a point. The distance between P and plane AX plus BY plus CZ equal to 0 can be calculated, let's just write D, can be calculated as capital D, or the distance, which is equal to Here we have a fraction. On the numerator, we have a times x1 plus b times y1 plus c times z1 minus d divided by square root of, we're going to divide that by the magnitude of the normal vector. A squared plus b squared plus c squared. The distance formula. So far we talked about the lines, we talked about planes, but we have some surfaces in the space. Some of them are very popular and they follow formulas. For example, when you have a surface like this, the name of that surface is an ellipsoid. The formula for an ellipsoid is x squared over a squared plus y squared over b squared plus z squared over c squared equals to 1. Recall that if the denominators are all the same, you get x squared plus y squared plus z squared equals to 1, which is a unit sphere. When they are equal to each other and they are equal to one number, we can multiply the denominator by that number, and then it's going to be x squared plus y squared plus z squared equals to that number squared, which is just a sphere with a radius. If you have a shape like this, we call it a cone. Equation of a cone is z squared over c squared equals to x squared over a squared plus y squared over b squared. When you have a shape like this, we call it elliptic paraboloid. As you can see, the cross section is a parabola. The equation for elliptic paraboloid is z over c equals to x squared over a squared plus y squared over b squared. Remember that in 2D we had parabola, and in 3D we call them paraboloid. We had hyperbolic functions, and now in 3D we have hyperboloid, but in space we have hyperboloid of one sheet and also hyperboloid of two sheets. For hyperboloid of one sheet, we get x squared over a squared plus y squared over b squared minus z squared over c squared equals to 1. When it comes to hyperboloid of two sheets, you get negative x squared over a squared minus y squared over b squared plus z squared over c squared equals to 1. So if you compare these two equations, x, y, they have positive signs, z has a negative sign. For hyperboloid of two sheets, x and y, they have negative signs and z has positive sign. And finally, we have hyperbolic paraboloid, which is like a saddle. The equation is z over c equals to x squared over a squared minus y squared over b squared. So comparing elliptic paraboloid with hyperbolic paraboloid, we can compare the formulas. z over c equals to, here you're adding x and y terms, here you're subtracting x and y terms. Well, suppose you have an object like this. Suppose they say, hey, you have z equals to 4x squared plus y squared. Okay, we graph this guy, and now we want to take a look at the formula sheet that we have for this object. So which one is this? Z is equal to 4x squared plus y squared. Between these objects, the formula z equals to 4x squared plus y squared gives us elliptic paraboloid. Elliptic paraboloid. The cross-section of elliptic paraboloid is parabola. Let's take a look at another object. Suppose we have x squared plus y squared divided by 9 plus z squared divided by 4, and it's equal to 1. What is this object? Well, okay, let's take a look at our set. As you can see, the object and the formula representing that object is an ellipsoid. X squared over 1 plus y squared over 9 plus z squared over 4 equals to 1, which is an ellipsoid.